So looking at general probability notes, starting out day one. Whenever we talk about probabilities, we need to be precise. So we're going to use these rules. A probability is a number between 0 and 1. If the event can't occur, its probability is going to be 0. That means it never happens. No way in any time can it happen. If the event always occurs, it's certain that it's going to happen, then this event has a probability of 1. I want to remember that 1 in decimal form of probability is the same thing as 100%. Okay? The set of all possible outcomes of a trial must have a probability of 1. So if you find the probability of finding a 1, a 2, a 3, a 4, a 5, or 6 on a dice, each one of those is a 1 out of 6 chance. So when you add all 6 of those numbers together, you would end up with a total of 1. Okay, so the probability that an event doesn't occur is 1 minus the probability that it does occur. Okay, so if we have a probability of event A, and it's a probability of, say, 20%, then the probability that A does not occur is the probability of no A would be 1 minus the probability that A does occur. So this would be 1 minus 0.2 or 0.8. Okay, now this is called a complement. Okay, the complement is the set of all outcomes when A does not occur, if you know the probability of A occurring. So we know A occurring is 20%, so the probability of A not occurring is 1 minus the 20%, or 1 minus 0.2. Okay, two events can't occur at the same time are called mutually exclusive. For two mutually exclusive events, A and B, the probability that one or the other occurs is the sum of the two probabilities of the two events. Mutually exclusive events have no outcomes in common. So if you look at this Venn diagram, this is mutually exclusive. Whereas here, you can see this area right here in the middle, they overlap, so they have some results in common. So this is called inclusive. So they are not mutually exclusive. Okay, so here's the rule in the formula. If it's mutually exclusive, you have an OR. So you have P, probability of A, plus the probability of B happening. Okay, it doesn't work if they are not mutually exclusive. So if we have this overlapping part, not mutually exclusive, then we have to do something else. Okay, and here is that. If we are looking at not mutually exclusive, if there is an overlap, then you must subtract out the overlapping information, the intersection of the two. Okay, this is the intersection, this little notation. It means both of them occur at the same time. Okay, so an example of not mutually exclusive. You're at a soccer game with the coach brought a cooler of drinks. There are 15 drinks in the cooler. There are 9 Powerades and 6 waters. So total of 15 drinks. We know there's 9 Powerades and 6 waters. They add to 15. Some drinks were just added to the cooler, so there are 3 Powerades and 1 water that are cold and the rest are warm. So there's 4 cold drinks, and that makes 11 not cold. So what is the probability of picking a Powerade or a cold drink? So the probability of a Powerade or a cold drink. So individually, the probability of a Powerade, we'll call it PA, is going to be 9 out of 15. or the probability of a cold drink. Call that a C for cold. Okay, there are 3 Powerades and 1 water, so there's 4 drinks that are cold out of the 15. Now, in the cold drinks, there are 3 of those that are both cold and Powerades. So that would be this part here, Powerade and cold. So we have to subtract that part. So we're going to subtract the probability of getting a Powerade that is cold. And there are 3 of them. So out of the 15, 3 Powerades are cold. So that would give me a total, add them together, that's 13 minus 3 would give me 10 out of 15, which is 2 out of 3 when you reduce it. So you have a 2 out of 3 chance, or 67%. Round it off. So that would be not mutually exclusive, where we have to subtract the value. Now, the other type are talking about independent and dependent events. Independent events occur when the probability that one event occurs in no way affects the probability of the other event occurring. So for 2 independent events, A and B, the probability that both A and B occur, now this is an and statement, okay, and is the product of the probability of the 2 events. Now remember, product means multiplication. So the probability of A and B occurring, drawing A, then doing B, is the probability of A times the probability of B. Now, you can extend this to more than 2 independent events. So we could have a probability of C, D, E, F, however many we want to go there. But remember, it requires that they are independent, okay, for this to work. Now, if they are not independent, then we have a slightly different probability. Okay, this is where they are called dependent events. This means that the probability of the second act depends on what happens in the first one. Okay, so for both A and B to occur, the probability A occur times the probability that B occurs, given that A has already occurred. So what happens here is we want to assume that we get A on the first draw. Assume what you want is gotten. And then that's going to affect what happens in the second event. Okay, so that's what this means right here. B, assuming A is already gotten. Getting B, assuming you already have A. That's what this formula means. Okay, now just to go back on probability, basic probability again. To find probabilities of equally likely outcomes, the probability is equal to the number of outcomes in the event divided by the total possible outcomes. So that's the probability of an event. So what happens in the event you want, how many times you can get that, divided by the number of possible outcomes overall. Okay, now when we are looking at a deck of cards, okay, excuse me, we want to remember a few things. We have 4 suits in a deck of cards, and I believe the next slide is going to show you all the cards. We have hearts, which are red. We have diamonds, which are also red. We have clubs. Some people call it the puppy dog one because it looks like a paw. And then you have your spades, and both of those are black cards. Okay, now that's 4 suits. And in each suit you have 2, 3, 4, 5, 6, 7, 8, 9, and 10. Those are your number cards. Then you have a jack, a queen, a king, and an ace. So there are a total of 13 cards in a suit. Okay, there's 13 cards in each of the 4 suits, so each one of these occurs in each of these 4 suits. That's a total of 52 cards. Okay, so what is the probability of drawing a jack, queen, or king from a standard deck of cards? Okay, so the probability of drawing a jack, a queen, or a king. Are these mutually exclusive? Yes, because you can't draw a jack and a queen if you're drawing one card. Okay, so the probability of getting a jack, a queen, or a king. So there are 4 suits, and they each have a jack. So that means there are 4 out of the 52 cards that are jacks. Plus, there's 4 out of the 52 cards that are queens. And there's 4 out of the 52 cards that are kings. Okay, these are often referred to as the face cards. Okay, so getting a face card from a standard deck of cards, drawing a face card, you have 4 jacks, 4 queens, and 4 kings. So that's a possibility of 12 out of 52. And if we reduce that, let's see, I believe that would be 3 over 13. And you can always do your reducing on your calculator to get your lowest term fraction. So that would be what we do. 4 jacks out of a total of 52, 4 queens out of 52, and 4 kings out of 52. Okay, here they are. So we have 12 cards total out of a total of 52 cards. So that's what we wanted to look at. This is, if you want to print this or off or whatever so you can have it to refer to, you can. Okay, so that is our notes for today, and looking at an example like this for your problem. We will be doing some practice on this tomorrow. You'll have a worksheet you can do, and please make sure that you have that last slide where you have all the cards on there, because it is something that will be important to look at.